I went to a talk on Friday, and they said that when students have professors that don't know how to use Zoom, it stresses them out. So at least because I'm looking at it right now, I'm being more extra careful to make sure that I have it like my face is on here. But I guess when I'm here in the classroom, I'm usually just more concerned about the classroom. But man, some people have like crazy setups for Zoom. I don't have that at all. I just use my camera and my computer, my laptop camera, my laptop microphone, and I don't have any crazy screen. Oh, here's Kiana. So, morning, Kiana. I went to tie me up yesterday.
Oh, you did?
Yeah.
I did too. I wasn't working.
You weren't working though. I mean, are you still
No,
working?
I only work Saturdays.
Yeah.
But I was helping train some new people though.
Cool. Yeah. I see Kiana tie me up in the food trucks. So anyways, so I guess it's time to start soon. Anybody have any questions about anything? So this week is normal. Next week is spring break though. So don't forget that but I'll remind you guys again. Okay, so this is where we left off. We're in acids and bases. So acids, and generally speaking, the way acids work is they add positive charge. Bases work by adding negative charge. So that's being, kind of overly simplistic there. Acids turn litmus red. They taste sour. You throw metals in them, they form hydrogen gas for most metals. Bases taste bitter, turns litmus blue. They feel slippery when you're on your skin. So just some qualities of bases. And water, we talked a little bit about water. Water is a weird substance. And one of the things with water is it's amphoteric, meaning it's both an acid and a base. It just depends. It can behave either way. It just depends on what its environment is. And what's even stranger about water is it reacts with itself. So, and this autoionization. So like autobiography is your own story. Autoionization, water will react with itself. And by this equation, I mean, you can do it either that equation or that equation, whichever one you want, but water will react with itself to form hydronium ion and hydroxide ion. So, and then the equilibrium for this is the Kw. So right, if you're going to write the equilibrium expression for this, it's going to be the H3O plus hydroxide all over water liquid squared, right? But you do not include the liquids in a equilibrium expression. So the dissociation constant for water, the Kw, is just the hydronium times the hydroxide ion concentration. And at 25 degrees Celsius, this equals 10 to the minus 14. So if the temperature changes, Kw changes. Doesn't change that much. Well, I should say if a human body temperature is 37 degrees Celsius, for instance. So it's a little different for human body temperature, but it's not that different. So it's not a huge difference. But that's Kw. And you probably colloquially know this. I'm sure everyone's heard of a pH before. So pH. So pH is here. What is the pH is the minus log of the hydronium ion, hydrogen ion concentration. And pH is a logarithmic scale. So meaning that each step, it goes up by a factor of 10. So there's other scales that are logarithmic scales. So decibels, like sound, that's a logarithmic scale. Each factor of 10 in decibels, similar to pH. Well, it's 1 for pH, but 10 for decibels, you go up by a factor of 10. So I'm talking pretty loudly right now. And I'm going to talk twice as loud right now. So I'm probably at about 75 decibels. So I'm just going back to my normal voice. And if I'm at, does that mean I'm at half as strong? Does that mean I'm at like 37.5 decibels then? Because I'm talking half as loud. No, I'm at like 73, right? So so if I were to scream at the top of my lungs, maybe I might break 100 decibels, probably not. But decibels work by each 10, you go up by a factor of 10 intensity. Also, earthquakes. So earthquakes, the Richter scale is logarithmic. So it works by displacement. I think it's every 10 to the minus 6 meters. So each step, so it started off with 10 to the minus 6 for Richter scale of 1, and then it moves up by a factor of 10. And the energy released in the Richter scale, it scales by a factor of 33. And that's just the Richter scale in some way is a model. They think there's like planes, like if you have it's modeled by, you have a flat plane, 2 planes, and how much these 2 planes shift against one each other. And if it's 10 to the minus 6 meters, I think is what the basis is. That's Richter scale of 1. If it's 10 to the minus 5 meters, it's 2, and so on and so forth. And it goes up by a factor of 30 because of the fact that it's you have behind these planes you have cubic rock, and assuming a constant density, I think of basalt, that's where the energy goes up. So Richter scale in some ways is a model. But anyways, pH is also a logarithmic scale, and it goes by the log of the hydronium ion or hydrogen ion concentration. We also have POH, and I'll show you some of the POH stuff later, but POH is just minus log of the hydroxide ion concentration. Has anyone heard of POH before? Out of curiosity? No, okay. You have? Okay. What's that? No, just the term POH. No, okay. But you've heard of pH before, right? Yeah, everyone's heard of pH, but POH is just like pH, but hydroxide, and the pH plus the POH is equal to 14. And some other rules with pH and POH, the sig figs are after the decimal point. So like a pH of 12.1, this has 1 sig fig because of the 0.1. So the 12 is kind of considered to be the exponent. So and then you can also go back and forth between pH and concentration. But here are some common substances with pH. So stomach acid has a pH of 1 to 3. Well, my stomach might have a pH of 1 to 3, probably closer to 3 right now. If your stomach's at rest though, if you're just sitting there, like if you probably by the end of class, or even maybe even 11 o'clock before I eat lunch, my stomach's pH is probably gonna be around 5.5-ish. So your stomach isn't always super acidified, because a pH of 1 or a pH of 3, that's the same pH as vinegar. That's pretty acidic. So it's your stomach is not always this way. It's just what your stomach acid when it's released is that way. So limes are particularly high in pH, and if you've ever I've had the unfortunate accident of cutting limes and then cutting my finger with the knife that I was cutting the limes, and man, that hurt. Because limes are pretty acidic. Same thing with lemons, these soft drinks, see these things, all these, and you can see here pretty much most food is acidic. And even bitter melons. Bitter melon you would think is alkaline by the name bitter, but it's acidic too. So pretty much all food is acidic. And you see rainwater. So rainwater, when it's saturated with carbon dioxide from the air, it has a pH of 5.6. So most water, so especially fresh water here on Earth, does not have a pH of 7. Oh, I didn't mention that. So pH of 7 is neutral. Anything less than 7 is acidic. Anything greater than 7 is basic. So and water here on Earth tends not to be neutral. It tends to be slightly acidic, at least fresh water. Ocean water, the ocean it tends to be alkaline. So the ocean is in fact alkaline at about a pH of 8.5 thereabouts. It depends on where you're at. It's variable. It's not consistent, but the average is around 8.5 pH for the ocean. Fresh water, it varies where you're at. But rainwater is fairly consistent with a pH of about 5.6. So if there's pollution though, you can get a phenomenon we refer to as acid rain. And acid rain, some of it is natural. We have here in Hawaii, we have terrible acid rain, absolutely horrible acid rain. Sometimes the pH of the rain is 3, so it's almost out of vinegar. So, anyone want to guess why we have such terrible acid rain? Volcano, yes, from the volcano. And some other types of acid rain is natural. So lightning storms generate nitric acid and nitrous acid, and that adds nitrogen to the soil. So some acid rain is good in that regards. But I mean, it's the anthropogenic, the human caused. And trees here, plants here in Hawaii, they're used to acid rain. It's not gonna be that much of a big deal. But if let's say that you are in the center of the United States, or you're in Colorado or something like that. Yeah, it is in the center of the United States. And you build a coal plant and you release a bunch of sulfur oxides in the atmosphere, and that causes acid rain. The thing is, the plant life there may not be used to it. So much of the native plants there can die from the acid attacking their roots. So, okay, that's rainwater. Blood. Human blood is slightly alkaline. It's close to neutral, but it's slightly alkaline. You can see the other thing. Egg whites, I said that most foods are alkaline or acidic, but there are a few exceptions. Milk of magnesia, that's magnesium hydroxide. That's no, it's not Tums. I'm sorry, Rolaids. And ammonia, a little more alkaline, and 4% caustic, 4% lye solution. So don't have bleach in there. I think bleach has a pH of about 11 or 12. So any more questions? But go ahead. It's going to be slightly acidic. It depends on how much you aerate it, and it depends. So here on Maui, it's let me think. We also chlorinate the water. So that's going to make it slightly alkaline. So, oh no, well, I guess I'm not sure, because it could turn I'm not sure. I don't know what the pH of the tap water is here. So it's going to be probably in the range of 5.5 to 8. I don't know, but I'm not sure. I always drink filtered water, so I don't know. My house is relatively new, and I drink the water from the tap. It tastes like I'm drinking from a hose. So at least, well, I shouldn't say relatively. It's like 4 or 5 years old, but still tastes like I'm drinking from a hose. So I can't really tell. Huh, I've never checked that. Is that something Google can tell us? What is the pH of Maui's drinking water? Oh, according to this, it's 7.2 to 9.1. So, because we have hard water, it says, okay. So I guess we have slightly alkaline drinking water here. So, of course, sorry, I know you can look up on Google yourself, but I was curious. Okay. Other questions? All right, so and I'm gonna mention a little bit about pOH every once in a while, but we don't have pOH here. The point of pH, so it's 10 to the minus whatever. So pH is 7. So the hydrogen ion concentration at a pH of 7, it's going to be 0.0000001. That's the concentration at 10 to the minus 7. And over here, pH is 0 is 1. You can have a negative pH if the hydrogen ion concentration is 10, the pH is -1. So you can have negative pHs. That's fine. So because it's minus log, the log of 10 is 1. Minus log of 10 is -1. So each step, though, the point of that is each step is a factor of 10 by its logarithmic scale. So look at this. A solution goes from pH 6 to pH 3. How much did the concentration of the acid change? How many think it's 2? How many think it's 3? How many think it's 18? How many think it's 1,000? Okay, raise a hand for 1,000. Yeah, 3 steps. So 10 to the minus 6. So you go 10 to the minus 6, 10 to the minus 3. That's a factor of 1,000. So that's a factor of 1,000. Does that make sense? All right, so let's do some calculations. Calculate the pH of each solution, indicate whether it's acidic or basic. So for A, this one is easy. You just go, the pH is just minus log of 1.8 times 10 to the minus 4. And that is going to be 3.74. And notice this has 2 sig figs, that has 2 sig figs. The sig figs are after the decimal point, and the pH of 3.74 is acidic. So there are 2 ways to solve B. So the first way you can do it is the Kw is equal to the hydrogen ion, hydronium ion. I like using hydrogen ion. And this is 10 to the minus 14 equals our hydrogen ion concentration. Actually, let's go ahead and write it. Hydrogen ion concentration times 1.3 times 10 to the minus 2. That means then that your hydrogen ion concentration is going to be 10 to the minus 14 all over 0.013, and then minus log of that answer. If you do that, that will give you 12.11. So that's one way to do it. The other way you can do it is you can do the pH plus the pOH is 14. So then, or 14 minus the pOH is equal to pH. So 14 minus a minus log of 0.013. And if you do that, you get 12.11. So 2 ways to solve part B. The book describes it in the top way. I actually prefer the other way. I like addition and subtraction better than multiplication and division. That's just myself. So it's whichever way works for you. And remember, the sig figs are after the decimal point. So the 12.11 pH has 2 sig figs. So questions on how to do either of these problems? So how do you go backwards? Get the acid concentration from a pH. It's just take 10 to the minus pH. So do you remember how that works with logarithms? And logarithms are just, the exponents are just the inverse of the logarithms. So this one's pretty easy. It's going to be 10 to the minus 4.8. And 10 to the minus 4. Oh, do I have that? Oh, here it is. It's just a one shot. 1.6 times 10 to the minus 5. I should put a 0. That's a 5. There we go. So that's how you go backwards from pH. 10 to the minus pH is the hydrogen ion concentration. So questions? Hopefully these are very easy. And I already mentioned the POH, and so not surprisingly, if you have a pH of 7, the POH is the same thing. If you have a pH of 14, the POH is 0. If you have a pH, the pH is 0, POH is 14. So they remember the pH plus POH is equals to 14 at 25 degrees Celsius. And this P, it just means that you take a log of it, the minus log of it. So the pKa is the minus log of the Ka. So especially next chapter, we'll talk quite a bit about pKa's. So, okay. So let's do another problem. Okay, so let's calculate. Why is this my screen not? Okay, I must have got sweat on my screen or something. So this is how you calculate concentrations using weak acids. So this example problem, what is the hydrogen ion concentration of 0.1 molar hydrogen cyanide? So the way you set up this is the same thing with an equilibrium expression. So you start off with initial change equilibrium, and you have 0.1 molar hydrogen cyanide, and then 0 of the dissociation products. So which way do we shift? We shift right. Minus X plus X plus X, 0.1 minus X, X and X. Ka is going to be hydrogen ions, cyanide, anion, all over acid concentration. 4.9 times 10 to the minus 10 equals X squared over 0.1 minus X. So this is an easy problem. How do you solve this? This is when you can use the X is small approximation. And you can kind of estimate this as X squared over 0.1. So that means 4.9 times 10 to minus 11 equals X squared. And you can solve for X. So this one, so 4.9 times 10 to the minus 11 is the same thing as 49 times 10 to the minus 12. So square root of both sides, it's going to be 7 times 10 to the minus 6 equals X. So and X also equals the hydrogen ion concentration. Is that right? Is it that easy? Let me see. Yep, it's that easy. So recap for this one, what is the hydrogen ion concentration of a 0.1 molar hydrogen cyanide solution? And there you're given the Ka value of the hydrogen cyanide, you look it up. So initial change equilibrium, initially 0.1 molar hydrogen cyanide, no products. So we shift right towards the products, one extent of reaction for each. And then we set up the equilibrium expression, the Ka value is equal to the unknown x, extent of reaction square root of a 0.1 minus x. And we can discount x because x is small and the bottom one. And then solving, we get x, our extent of reaction equals 7 times 10 to the minus 6. That also equals the hydrogen ion concentration, so we can stop there. Questions with this one? Okay. All right, so let's see if you can do this one. What is the approximate pH of a 0.2 molar so it's nitrous acid solution? Here I can move this down. So don't know what to do. If you don't know what to do, you start off by writing the hydrolysis reaction. You can do it one of two ways. You can do HNO2 plus water in equilibrium with H3O plus NO2 minus. So that's one way to do it. Or you can write HNO2 equilibrium H plus NO2 minus. Either one works. So just seeing where you're at. How many think it's A0? I think it's B1, C2, D3. Okay, so still working. Okay, I'm gonna come around. Kiana, do you need any help? Are you following? Just doing our own.
I think I'm okay right now.
Okay. All right, I'm gonna check on the students in the classroom. Send, drop me a chat or yell at me if you need anything. That's not, I'm sorry. Yeah, it's fun. Yes, that's a 4 out of 9. I can see why you it's 9. There's 4.6 plus 7 minus 9 times. Well, the good news is you're getting the setup right. Your guys' setup is right, and that's the hardest part. Yeah, you guys actually you got the setup right. You got the setup right, which is the hardest part. By far the hardest part. So no. But it's just that's one thing that sucks about chemistry, right? You just screw up one little step and it throws everything off. Which is why people hate chemistry. Or at least this class. Because how could you hate chemistry? It's like it's impossible. So, but here's the set. Do you guys have any questions? How about you, Kiana? You doing all right?
I'm doing good.
All right, well, obviously answer C. All right, now moving along. So now, as is typical fashion, right, I kind of go through a couple different types of problems to try and kind of get your skill base kind of set up. So let's look at this one. A 0.1 molar weak acid solution has a pH of 4.25. What is the acid dissociating constant, the Ka for the acid? So if you can imagine this, you're going to have 0.1, 0, 0. So you're going to shift right. And then 0.1 minus x, x, and x. So your Ka is going to be, it's going to be x squared over 0.1 minus x. And now you're like, okay, what's my x? Well, you know that the pH is 4.25. So you know that your hydrogen ion concentration is going to be 10 to the minus 4.25. So what is that? Let's see here. Shift 10 to the negative 4.25. And I wish this thing had a scientific mode. Well, I guess I can turn it to mode. Oh. It doesn't want to change anyways. How many zeros? So it's going to be 5.6. The six figures we have 2, 5, 1, 2, 3, 4, 5. It's 10 minus 5. Okay. Yeah, my calculator says floating zeros and trying to count the zeros. So, all right. So now what you do is you would plug that back into here, where your Ka value is, of course, going to be your hydrogen anion over the acid. It's going to be 5.6 times 10 to the minus 5 quantity squared all over 0.1 minus 5.6 times 10 to the minus 5. You could probably even discount that if you want. So what problem is this? Oh, and I'm looking at the book. The book discounts it. The book just does the approximation. And the book says 3.1 times 10 minus 8. So like so. So, and one of the reasons why I'm showing this example, among other things, is, I mean, ice charts, they're wonderful. They're great things, but remember that you, the user, need to take the information and interpret it. So I know that I'm kind of carrying you up to set, like, okay, now I need to solve for X, but like, what's my Ka value? Well, you're looking for the Ka value, but then you're hunting for hints. And then this pH of 4.25 gives you that extent of reaction, because it gives you, it'll tell you what the hydrogen ion concentration is. Well, it'll tell you this at equilibrium. So using that information then and the setup from the ice chart, you can then figure out what the Ka value is. So recap for this one, 0.1 molar weak acid solution, pH is 4.25. What's the acid dissociation constant? So one of the ways you could set this up is write the ice chart and you shift right. So you lose an extent of reaction for acid, you gain an extent of reaction for the hydrogen ion and anion for the acid, and its conjugate base. And then you have the equilibrium expression where you have the extent of reaction squared over 0.1 minus x is the acid dissociation constant. You can discount the X if you want, but the pH tells you what the extent of a reaction is. So then you plug in the value using the pH, you get the hydrogen ion concentration, which is also going to be the extent of reaction. So extent of reaction squared over 0.1 is, and then you get 3.1 times 10 minus 8 for the acid dissociation constant, the Ka value. So question with that one? You're squinting, or is it, or are you thinking? Is it hard to see? So, other questions? All right, next is percent ionization. And I mentioned, I was trying to be really sweet by saying my wife and I on our honeymoon were like weak acids, because we were always very, very close together our whole honeymoon. I mean, we're still close now, of course, but you know, particularly on our honeymoon. And so, but we weren't together all the time. You know, we went, so, but that's the way weak acids are. They like to be together. And let's see what the percent ionization of 2.5 molar nitrous acid is. And so another common sense thing, the percent ionization is how much it breaks apart divided by its original amount times 100%. So that fraction of what breaks out over its original amount times 100%, that's going to be our percent ionization. So again, good old ice chart, you know, probably almost a knee-jerk reaction at this point in time, like reflex, which is fine. So start off with some acid, no products, so we shift right, minus X plus X plus X, and then 2.5 minus X, 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 right? So our Ka is going to be products over reactants equals 4.6 times 10 to the minus 4, which is given, which is X squared over 2.5 minus X, which we can approximate as X squared over 2.5. Then, so then we have X equals, well, let's just say X squared equals 2.5, 4.6, oops, times 10 to the minus 4. And we can get rid of the square by taking the square root. And doing so, X equals 0.034. So now we have, that's how much is dissociated. So we have 0.034 that's breaking apart over 2.5, and then that times 100%. So in doing so, this equals 1.4%. So, okay, recap for this one. So we want to figure out the percent ionization of 2.5 molar nitrous acid. So percent ionization, so it's like kind of like if you wanted to see like, well, I guess I already used the honeymoon example. I just how much of it, whatever breaks apart. So how much of it is going to ionize? How much does it fall apart, and compare how much it falls apart versus its original amount. So that's we would consider that to be chemistry, science, math, common sense to have that. How much breaks apart divided by its original amount, that fraction times 100% is going to be your percent of breakage. So how we figure out how much it falls apart, though, we got to do the initial change equilibrium, write the ice chart. So initially 2.5 molar nitrous acid, no products. So no products, some reactants means we shift right. So we lose an extent of reaction of acid gain, a extent of reaction for each product, and equilibrium value 2.5 minus x and x for the products. And our acid dissociation constant is going to be products over reactants, given it's 4.6 times 10 to the minus 4. From the ice chart, it's our extent of reaction unknown x squared divided by 2.5 minus the extent of reaction. So then we can estimate that by discounting that x, and we get x equals 0.00 or 0.034. So for nitrous acid at 2.5 molar concentration, the equilibrium concentration for the hydrogen ion is going to be 0.034. So that is also how much it breaks apart. So take that 0.034 divided by the 2.5 molar that it was originally, times 100%, and we get 1.4%. Which means then this is a weak acid. It's a weak acid. It means 98.6% of the time it's together. And 1.4% of the time it's broken apart. So that's also why, so weak acids are also known as weak electrolytes. If you remember that from chemistry 161 or first gen chemistry, wherever semester, or if you went to a different college. So over 98% of the time, it stays molecular. So weak acids like to stay together. They don't like to break apart. They like to stay together. Only occasionally do they ionize. But that occasional ionization does cause problems. So one of them is, it's that hydrogen ion then can then go attack things. It can also, you also can have a weak electrolyte solution from that. So questions with this?
I have a question.
Please.
Sorry, if you scroll up a little bit. You mentioned it before, but I'm just not like fully comprehending. You know the part where it's 2.5 minus x. How come we dropped the minus x again? Is it just like so small you don't need it or something?
Question was, why do we drop the x, the quantity 2.5 minus x? This is an approximation. So this step here. So what you're saying is, it just makes your math easier. So let's say you didn't do this, and you're welcome to do it. So let me change colors. So let's say we didn't change it, then you're gonna have so you're gonna have 4.6 times 10 to the minus 4 equals x squared over 2.5 minus x. So then you're gonna have to FOIL this. So you're gonna have whatever 2.5 times 4.6. So right, you're gonna have 2.5 times, I should do the 4.6 times 10. I'll just keep the numbers, minus 4 minus 4.6 times 10 to the minus 4 x equals x squared. So then you're going to have x squared plus 4.6 times 10 to the minus 4 x minus 2.5 times 4.6 times 10 to the minus 4. Oh, no x equals 0. Then you have to do the quadratic equation, right? So it'll be x equals negative 4.6. I'm just going to call this, well, I won't put it all in there. It's the negative b plus or minus the square root of 4ac. Oh, no, I'm sorry, b squared. B squared minus 4ac all over 2a, right? You have to do that then. And it'll work, but it's just a bigger pain in the butt. But if you get rid of this value, if you get rid of that x value there, you don't have to do the quadratic equation. So it's a lazy skip step. You can do that. And do you have a really sweet calculator, Kiana? Do you have like one of those like graphing calculators with a solver function?
No, my calculator like is dead half the time. I do
Okay.
not.
Yeah,
I'm
I mean,
like,
since if
yeah,
you
no.
want, I mean, like if you have one of those sweet calculators, like just you could just put this expression in and then like do the do the solve whatever solve y1 comma x kind of thing, and it'll spit out the answer.
Damn.
you know
Might buy one. Nah.
if you but I mean doing the foiling and then quadratic equation, that's just, I mean, and if you do that, you're probably gonna get an answer really, really close to x being 0.034.
Okay, and so anytime that it has that negative x, I can just drop it.
Um, it depends on the context. For this class, yes.
Okay.
With the exception of, I'll talk about it. Like we're going to get to sulfuric acid. For sulfuric acid, you can't. But for this class, it's almost always yes. In fact, it usually tells you like you can't do the x is small approximation.
Okay.
So and it only works. So it only works when you relate the number to something else. So because so this number here, the 2.5 minus x, you're just saying that the x is small, that I can just discount that. I mean, if you do the x is small up here, like, well, you know what, we'll just discount this x2, and it's about 0, which is true, but then you get 0, you end up with a mathematic fallacy where you say 4.6 times 10 to the minus 4 is 0, and that's not true. You can say it's approximately 0, but that still doesn't tell you any information. But this one here, discounting this x here, that will make your life a lot easier mathematically.
Okay, thank you.
Yeah. Other questions? And again, it's only when you relate it to something else. So no, and sorry, I keep on repeating myself, but it's just it's like it's weird. It's weird. I mean, like you're so used to doing math and like and making it all pretty, and you get to chemistry where we're still in academia and the numbers are pretty, but they're kind of weird. And now we're starting to do these weird sort of like shortcuts. And part of it though is because up until the 1940s, we didn't have computers. So I mean, the first computer that would do calculations, where they were invented in the 40s, and like they were as big as the room, right? So I mean, it was they were just huge. And you actually had people, their jobs they were known as computers. People had a job called computers. Like you would do math all day. And like and since we didn't have like I mean, the thought of having a device like this that that can figure out that you don't need to have a logarithm tables with you, you can just do just about any calculation you want at your fingertips. That would be super awesome sci-fi for someone in the 1940s. So, and all these ways of doing things, the quick math, it's, I mean, in a way, I mean, we're still teaching them, but also a lot of the equations that we use. So next chapter, we're gonna get into something called the Henderson-Hasselbalch equation. That one incorporates the x is small approximation for that. And another equation I mentioned, E equals mc squared. That also includes some x is small approximations in that as well. A lot of heat transfer that you do in fluid flow heat transfer terms in engineering. If you go into engineering, those terms go away with x is small. So you will see, depending on your field of study, you will see this again. So, all right, sorry for the long tirade on the awesomeness of things. Okay. So I want to mention the common ion effect. And So what do you do? We'll get into more of the common ion effect next chapter, but where we see it is in mixtures of acid. So consider a mixture of acid that's 0.1 molar hydrochloric acid, 0.1 molar in formic. Is that formic acid? Yeah, formic acid. And so problem with with this thing is that if you have three things, if you have hydrochloric acid, you have formic acid, and you have water, you have three sources of hydrogen ion. So how do you deal with this? And when you set up the equilibrium, you have to look to see what the common ion is. So, and since with this mixture here, so hydrochloric acid is a strong acid, meaning it completely breaks apart. So it completely breaks apart. And so when you set up the equilibrium then for formic acid, so formic acid, this is formic acid, and have the hydrolysis reaction. Hydrolysis reaction means reaction with water. And so the initial concentration of formic acid is here, but the difference is you have to include the common ion, the acid ion. And you still have the shift right. So you have a zero here. There's a zero here. It's easy when you're doing shifts. If you have a zero on one side of the equation, you're going to shift towards that side. Let's say you have zeros on both sides of the equation. It means the reaction is not going to happen. So if you have a zero, though, if you have a zero on one side and you have things on the other side, you will shift towards the zero. So we're going to shift right. And one of the differences, though, you can see that you have the acid, the hydronium ion or hydrogen ion concentration. You have to include that in the equilibrium. And so this is referred to as the common ion effect. So the common ion effect. And so kind of like, I mean, think of it when you meet someone. Whenever you, at least for me, like when you meet someone, one of the most common things you do, you look for commonalities with someone, right? You come up to someone and like, maybe if I never met Kiana, I'd be like, hey, have you ever heard of this amazing restaurant called Tie Me Up? Like, is that something we have in common? She works at Tie Me Up. That's why and her uncle owns it. But so that's something, we have in common. We both like Thai food, so likewise, what do hydrochloric acid and formic acid have in common? What they have in common is that they both make hydronium ions or hydrogen ions, right? So they have that in common. And since they have it in common, when they meet up and then they do math together, those common ions have to have a place in the setup for the equations. So that's the importance of the common ions in this. So you, the chemist in training, has to spot these common ions. So does that make sense? Yeah, Dennis. You could. Well, this one, the problem if you did that, if you ignore these two x's, the ones already highlighted, you will get x equals, okay, no, that's actually, you can do that. Yeah, that's fine. You can still ignore it. And in doing so, you get x equals to Ka. Yeah, so it's still, this approximation still works. And I know I've already highlighted it, but I'll highlight it again. Getting rid of those x's, because x is small compared to that. And so, and from this, you get x equals 0.00018, right? So, and that's pretty small compared to 0.1. So yeah, it shifts right, but not very much. And if you haven't noticed though, when you have mixtures of acids, it almost doesn't matter. Like the formic acid is going to be inconsequential. The pH change from the formic acid, it's not gonna, it doesn't really change the pH really at all. So it's hardly noticeable unless you have, that level of discernment in your measurement ability that you would need to have at least 4 sig figs, and 4 sig figs on pH is huge. I don't know. I don't know of any machine that could do that. So where it does matter is, and we get to sulfuric acid. Okay. So other questions? All right. So I'm gonna shift and I'm gonna talk about strong bases. And this is what the book considers strong bases. What's weird about chemistry, we'll say one thing and then we'll say in a different context means something else. So the textbook, for instance, so it calls these a strong bases: lithium, sodium, potassium. We can add a few more. They're not as common, but rubidium hydroxide and cesium hydroxide. We could even call francium hydroxide, even though francium only exists for a microsecond, right? And where am I getting these numbers from? I'm getting it from the periodic table, right? So you can see there lithium, sodium, potassium, rubidium, cesium, and francium. But I mean, francium, it's not very stable. So, and again, these metals are called the alkali metals, the alkaline metals. What does alkaline mean? It means basic. It means not acidic. So all of these metals, if you throw them into water, you get a very strong solution. The book also says calcium, strontium, and barium hydroxides are strong acids. It doesn't say that magnesium hydroxide is, or beryllium hydroxide. So personally, I don't consider calcium hydroxide to be a strong base. So, well, I guess it depends. You can drink this stuff. So you can take a saturated, it's called lime water. You can take a saturated calcium hydroxide solution, you can drink it, and you can actually use it to calm your stomach. So I probably wouldn't do it with strontium. I definitely wouldn't do it with a barium hydroxide, because barium is also very toxic. So, but I mean, but also calcium hydroxide, you don't want to put this in your eyes. It'll hurt your eyes, but it'll calm your stomach. So it's kind of borderline, what you kind of consider to be a strong base. But soon we're going to talk about salts. So salts being the result of an acid-base neutralization reaction. And alkaline earths, in terms of salts, are considered to be strong bases. So this is, I can appreciate you as a student saying, like, what the heck is going on here? You tell me that alkalis are strong bases, that works all the place, but then alkaline earths, some of them are strong bases and some of them aren't, and it depends on the context. So I feel you, it's weird. And so keep that in mind. Again, but the calculations work, because when we do these, like with calcium hydroxide or something like that, we will have the equilibrium values. It's just saying that, I mean, the alkali metals, they're really strong bases. They're very strong electrolytes. These ones here, maybe a little bit, but the textbook can be kind of confusing in that, because they do change their attitude. And it's not just a textbook, it's just the way that we teach general chemistry, unfortunately. So here are some weak bases. So carbonate anion, and there's the KBs. You can see, oh, you can see the words amine. So amines, and I mentioned this when I talk about vitamins, vital amines. The word amine, that's a specific, it's an organic molecule that has a nitrogen in it. And there's a lot of, and these are, the ones I've highlighted in yellow there, those are all amines. And you can maybe even, you can think of other words like amphetamine. What the heck was that? Is that a bird or is that from my computer? Anyways, sounded like a recording. Anyways, besides the fact that I apparently am hearing bird voices in the room. So here's some weak bases, but similar to strong acids, and I told you to memorize the strong acids. Strong acids are hydrochloric, hydrobromic, hydroiodic, not hydrofluoric, nitric, sulfuric, the first hydrogen sulfuric, and perchloric. So if you remember the strong acids, there's only a few of them. Everything else is a weak acid. Then compare it then to the strong bases. The strong bases are the first two columns of the periodic table, kind of, sort of. Maybe not the second column, but definitely the first column. If it's a base and it's not in those, and it's not in one of the first two columns of the periodic table, it's a weak base. And what does it mean to be a weak base? It means it's not a strong electrolyte. So, okay. So let's do some of these calculations using bases. So finding the OH minus and pH of a strong base solution. So what is the hydroxide ion concentration, the pH of each of these? So 0.225 molar potassium hydroxide. Again, there's two ways to do this problem. So you can do it as you can do your hydrogen ion concentration, hydroxide ion concentration is equal to 10 to the minus 14. I should make it a little prettier. Minus 14. So that means your hydrogen ion concentration is going to be 10 to the minus 14 divided by 0.225 molar, and then minus log of that answer. You can do it that way, or what I would do, what I prefer, is I do the POH is going to be minus log of 0.225. I can even, so minus log 0.225. So this equals 0.647. And then 14 minus 0.647 equals 13 point, how many sig figs? 352. And so this is our pH. And so, well, pH is equal to the pH plus POH is 14, which means that 14 minus the POH is the pH. So I calculated the POH, 14 minus the POH is the pH. So either way you want to do it, I prefer the addition method. The other method will work just as well. Now, then let's do the same thing for strontium hydroxide. The difference is that 0.0015 molar strontium hydroxide, there are two hydroxides. So our hydroxide ion concentration is twice the concentration of strontium hydroxide. So then you have the same idea. The the POH is minus log of 0.003. 14 minus, I guess it'd be, well, minus the POH. So it would be 14 plus the log of 0.003. And how many sig figs? 2. This is going to be 11.48. So are you seeing my logic on how to do these? Okay. How are we going to time? 10 minutes. Do I have enough time for this? Sure, I can start it out. Or is anybody having a question that can consume 4 minutes of time? I'll start with a setup and then I'll promptly erase it. So what is the hydroxide ion concentration, the pH of a 0.1 molar ammonia solution? So one of the things you should know, you are the chemist in training, you need to write the hydrolysis reaction. Hydrolysis reaction is the reaction with water. So this is something you should know how to write. That looks horrible. So that's the hydrolysis reaction. It's a reaction with water. And then initial change equilibrium, 0.1. Water is a liquid not included, 0, 0. We shift right. So 0.1 minus x, x. Our KB value now is going to be the products. All over the reactants. And then we put in our numbers 1 point, oops, that's a 7. 76 times 10 to the minus 5 equals x squared over 0.1 minus x. And again, if you want, you can discount the x. 1.76 times 10 to the minus 6 equals x, and so, or x squared. So then take the square root of both sides. I guess I do have time to solve this problem, but I'll the numbers. So we can solve for x. X equals 1.33 times 10 to the minus 3. And it wants the pH of this. So, which also equals the hydroxide ion concentration. So that means that that's 14 minus the POH, the pH. So it's going to be 14 minus a minus log of 1.33 times 10 to the minus 3. And you do that and you get 11.124. I know I flew my way through this. I think I'll erase this and pick up here on Wednesday. But I'll just want to give you a quick preview. Or did you guys follow that, or is it just no? You look okay. Looking at your faces, you didn't. I'll pick up here, and we got 1 minute left. I didn't want to give 4 minutes of chemistry jokes though, or something like that. So, all right, I guess there's less than a minute left. Anybody have any questions? Nope. Oh, and I guess I should mention on Wednesday, I have to go to a meeting right after class. So unless you really need something, I'll be back in my office later after the meeting, but for about an hour. It's an accreditation meeting. I was invited to come. Actually, I have to take a COVID test soon because they only let people that have COVID. They're making everyone take a COVID test. So, but I'll be busy right after class on Wednesday. So anyways, all right, that's my shut up alarm. So it's time for me to shut up.